We're going to have a talk by Dion. Dion is greatly known within the embedded community for many crates. He's probably going to talk about one of these crates. He has two very cute cats. We'll give a great hand to Dion.
Thank you. Move the slides. Yes. Okay. Hello. Thank you. Welcome for joining me. Yeah, I'm gonna talk about my device driver toolkit. I had to come up with a title, so it's Codegen Your Problems Away. That sounds nice, I think. First of all, what this talk is not is like a full guide on how to use it and an explanation of all of the details. If you want that, there's a lot of written docs. I'm gonna link to it in the end, so just so you know. So, who am I? I am Dion, 28. I've got some cats, like Wouter said. I'm also the embedded tech lead at Tweede Golf. I've got some crates and I do some contributions in some places. If you want to follow me, I'm Dion Dokter pretty much everywhere. So yeah, maybe don't follow me on GitHub. That's a bit of a weird feature, I think, but do what you must. So I'm taking you back to winter 2019. I was graduating, and in my school that was with an internship. And I was writing embedded C++, and we were very, very forward. We were using embedded C++ 17 in 2019. So you think we're 2 years behind. Actually, we were living in the future, but the numbers, like, don't look at them. But I was wondering, like, is there not something better than this? Because sure, it worked. It was fine, I guess. Well, we were using CMake, maybe not that fine, but is there not something better? So I started looking around, and I found D. I discovered D, and I looked at D, and I thought, like, wow, this is much nicer than C or C++. But, like, whenever I look at the forums, like, nobody seems to be using this. Like, there are a couple of people, but most threads are, like, from 5 years ago and had, like, 2 interactions. Why is nobody using this? And then I found the answer. Somebody said, it's not better enough to warrant a switch. And that kind of makes sense. Like, it was better, but maybe not that much better. So disappointedly, I went on. I had sort of given up. Like, maybe C++ is the best that it's gonna get. Luckily, I did not fully stop looking around, and I found Rust in the summer of 2019. Still the same question, like, why is nobody using this? But the answer here is very different because it was still very new. Like, maybe not to some of you people here, but like in general, to the general public, it's still very new. So this was nearing the end of my internship, and I snuck in some time to read the book. That's the one of the pros of using Jira and Scrum. Like, if your tasks are done, like, well, just read the book. And Rust seems great. And I read Rust, and I think, like, whoa, hold on. You can just run cargo run, cargo doc, cargo fund, Rust up update, and everything just works. This is pretty amazing. Like, wow. This was like world-shattering to me. Like, I was coming from C++ with CMake, with manually installed GCC ARM compilers, and like, ugh, this is great. In the fall of 2019, I was done with school. I had my diploma, and I was joining my first job. It was at a C# shop, so I was expecting to do a lot of C#. But instead, I was put on the innovation team. Well, they say there is no I in team. There is an I in innovation team, and so I was the only one really in the team. In the end, I, had to make an embedded product. And I asked if using Rust was okay, because I had previously learned a little bit about it, never really used it, but well, it's looking so great. And everybody shrugged, like, well, you're the weird guy on like the other team, and like, we don't do embedded, so everybody shrugging was enough of a yes for me to like just do it. So I start looking into running Rust on embedded, and I was like, hold on. You can do cargo run, cargo doc, cargo fund, Rust up update, and it just works on embedded without having to use horrible vendor tools. And also, we're getting logging for free. This is so amazing. Like, I don't know what the hell is making this all work, but like, I don't know, it's magic. So I create my first application. I'm looking around for some crates. And hold on, again, please, this is the last one. We've got generated packs to be able to interact with the microcontroller. We've got embedded HAL, which is the glue of the entire embedded Rust ecosystem. We've got type safety, good open source hardware abstraction layers. So it's not possible to call set high on an input pin. Like, that doesn't make sense. Arduino. And with all of this, we can build platform-independent drivers. So Rust amazes on every level. I really want that to sink in. Compared to where we came from, everything is amazing. But on this journey, on my journey, so far at least, ooh, foreshadowing. Because this talk is about device drivers, and so let's look at how we build a device driver. In this case, what I mean with device driver is on embedded, you've got a PCB, you've got a microcontroller, and it's connected somehow to like a sensor or something. That sensor we call like a device, and we want to build a driver for it. So in C, we've got like an enum containing all of the registers and the register addresses. We've got some definitions for masking and bit shifting certain values out of the registers. We need to be able to actually read a register and also like write, and it's not great, I think. Like, if we get a value out of this, we need to bit shift it and mask it, and well, then we look at the Rust code. It's very similar. It's a little bit longer. It's longer for a good reason, because we are actually using this embedded HAL trait right here. So what we've written here is cross-platform, so that's nice. But then the basis, it's like the same as what C is doing. And I was just like, Rust is better in every way. Like, So I think a good device driver should be kind to its users. So you really don't want your users to have to do bit shifting and masking. So for every field, you should really provide a function like this, where you do the read, so the user can get the value. And in this case, there's also a manufacturer enum, so people don't get like manufacturer 12. Like, what does that mean? You get an actual enum. Like on this chip, the DW1000, this is from the datasheet. We have 140 pages describing all of the registers and all of the fields. And I've counted them up, and it's about 400 register fields. So we need 400 getters, 400 setters. I don't want to write that. Neither did the author of the DW1000 crate. I'm picking this chip because this is actually what I was looking for. And there was a Rust driver. And the author of that Rust driver turned out to be a genius, Hannah Brown. Because he was looking at the same thing and also thought, I'm not going to write all of those registers. So what he did is he created a macro which gave him a sort of shorthand syntax to describe everything. And this generated a bunch of the code for him. And he also did it in a really smart way, because he defined this reg accessor. And this is, like, it doesn't really do anything on its own, except for being able to read registers that are readable, write registers that are writable, and being able to modify registers that are, well, both. And this gives the same syntax as what we're used to on normal embedded Rust with the so-called packs, so we can interact with our microcontroller, but now also for our device driver. So we've got some generics here. Most important one is this R, which is the register. For each register, there is a generated struct, and so this manages the buffer of this register. It also has an R and sometimes also a W struct, which is a reader and a writer. And those then define the actual getters and setters of all of the fields in the register. So this is what it looks like in usage. This is from the actual driver. And we can see we can read the status, we read it, and then we can access the fields and compare things and write stuff back. And this is way nicer than having to, like, just imagine that you read the status here, and then you and it and shift it by all kinds of weird values. This is much, much nicer. And so when I saw this, that good feeling was back. Like, hey, actually, this thing that I thought like maybe sucked in Rust can actually be done well. But currently, this is only part of this DW1000 driver. It should actually be liberated out of here. Maybe all drivers should be written like this. I don't know. And so I did some of the work. So in September 2020, I released the first version of my device driver crate. This is actually already sort of the second version, because I wrote something very similar like privately in the company. But then later I recreated it and like open sourced it. And I made a couple of changes. It's not just a copy. First of all, I think the syntax is a bit nicer. I've got access modifiers per field, so you can have a read-write register which has a read-only field, for example. There's also conversions. In the DW1000 driver, everything was still numbers, but here we can actually convert to something. And as a user of this, you had to implement this trait and give it to the driver, so it actually knows how to read a register and write a register. So this was also a way to make it generic for any kind of chip. You decide if you use I2C or SPI or whatever. But over time, some problems started to creep in. I wanted more features. I wanted to have endianness support, because some chips are big endian, some chips are little endian. Some chips, in theory at least, also do most significant bit first. Very cursed, but it could exist, and I wanted to support it. And all kinds of stuff. After adding all of the features, I wound up with having a crate containing 8 macros with in total 32 macro branches. Oh, did I mention they also all call each other in weird ways? It was a jungle. This, on the top here, this was the top level macro. If you don't know what's going on, well, neither did I at the end. So adding new features was very, very difficult. And I still had so much more I wanted to add. Also, some people said like, well, I would want to use it maybe, but I would rather specify it as like a text file, so I can grab some documentation and transform it into the correct format. They also wanted to have a CLI, so they didn't have to use macros, but instead could generate it ahead of time, which could save compile times. And also commands and buffers, like a command is different from a register. You might use a register to write a value, but then issue a command for a radio, for example, to like start listening or stop listening, start sending. That's a command. And the buffer is like a FIFO buffer. So again, on a radio, it could be the buffer you write your message into before you send the start command. I didn't really want to add this to that crate. So what do? You rewrite it as a proc macro. This idea was there very early, but I only executed on this like, I don't remember, 2023 or something. And in early 2024, I had finished that. It was a lot of fun to learn. I added all of the features I wanted, so pretty much was a successful rewrite. The syntax changed again, still similar, but you could do strict conversions now. So it checks if the enum actually is valid for all of the bits that are possible. You now had to preface this with the register keyword because, well, there were commands and buffers now as well. I even added async because that was like hot and new. So this is a dummy test device, and you could implement your YAML on this device, and it would generate all of the stuff. And yeah, here you see some of the commands and the buffers. And I was happy. Like, I'm out of the jungle for half a year. There were still more problems this way because, like I said in the previous slide, it actually still had the same structure, mostly, as the old macro had. And yeah, so there was not very good error reporting. The syntax was inflexible. Like sometimes you couldn't reorder stuff, even though like you should be able to. Very little testing, so that's another reason why adding new features was kind of difficult. But this was the most difficult part. There was a one-on-one mapping of the input to the output. So if you define a register, it'll generate a register for you. But this guy, Alex Moon, came with a PR that screwed everything up. I did accept the PR though. He wanted to have blocks of registers, because some chips are modeled this way, where you have like repeating blocks of the same registers. And also we came to the conclusion, like it would be very nice to be able to like sort of copy a register, but override certain values. So suddenly I needed to add inheritance, and like blocks like are kind of namespaces. So let's rewrite it again. It's still a proc macro, really, but this time rewrite it using the inspiration of a compiler. Now, I'm not a compiler engineer, but I know roughly what a compiler looks like. And, well, yeah, everything is a compiler, right? But this certainly is. Like, you take an input, give an output. Okay. And this is the new structure I came up with. There are two sort of front ends to this compiler. I've got the DSL, which I sort of inherited from the earliest version. And I also have YAML, JSON, and why not, it took 5 minutes to add TOML input. These are serialized or deserialized using their respective crates, so I get a value enum from them. The DSL is parsed by SYN and then parsed by me into like some high-level representation. And then both of these are transformed into like sort of like, I call it mirror, maybe that's a bad name, I don't know. So this way I was able to clean up the different front ends. These are now separate from each other. But the real magic is happening here because this layer is new. Previously, I went from my like middle representation immediately to the output. hence the one-on-one mapping. But now I put this layer in between, and I can do a bunch of things here. I can do rule checks. So if two registers are at the same address, it actually comes up as like an error, like, hey, you probably didn't mean this. I can also check if names are unique and all that kind of stuff. And I could duplicate stuff. So if I have a register and another ref register, I can actually just act like that's two different registers. I also wrote a book specifying everything you should need to know about the device driver and how to use it, even down to like how the syntax works in like a sort of self-thought-up grammar that kind of looks like the way Rust specifies its grammar, but like it's not the same. I added a bunch of tests. 97. This is the code coverage. It used to be a little bit higher, but like this is still pretty good, I think. So yeah, I can now actually add features or change things and be confident it doesn't really mess up anything. And this is now the new structure. I have a proper global config. Commands actually have data just as registers have, and this logic for parsing this and using all of this is the same as for the registers. So it was really nice. And I thought this was nice enough to call it 1.0, which was released in December. When using it for a new driver, which I wrote myself, I just call a macro, give it my YAML. My YAML is 2100 lines long, and it generates 18,000 lines of Rust, which, well, is nine times roughly more code. But most importantly, this is all code I didn't have to write. I only need to write like the 10-ish% of the code. And that's really the goal. Not having to spend a lot of work while getting a really good driver out of it. There are other users as well. Funny thing is, way at the top is Wassassin, which is our MC over here, Boutel. But what I think is the coolest is there is this weird organization, Open Device Partnership, and if you go dig into that's actually Microsoft. So Microsoft is already using my device driver crate, which is really cool, I think. Who knows where it's actually being used? There's a bunch more to do. I want to add a memory object type, which is like, we have a buffer, which is like a FIFO queue, but memory is like a random access. I want to do multi-register reads and writes, because that's happening in a lot of software. I currently don't support that, and looks like it's blocked on having more const generics, sadly. Dynamic length for commands. Oh, this is also actually fun. I found out Cuddle exists, and it looks pretty nice. So right now the input languages are YAML, JSON, and TOML. JSON is horrible to write. YAML is cursed. TOML, like, I really only added as a joke. You don't want to write your device driver in that. So, like, no option is perfect, and like the DSL is like a DSL. So maybe I should look into Cuddle. I don't know. And there are more possibilities to make it like even better in the future. Like currently, it only specifies what the device is, and not really what it does. So we have a list of all the registers there are, but device driver doesn't know how to actually read and write to the device. The user has to specify that using a Rust trait. But if you implement that in the YAML, for example, and you also specify how you do device init, well, then actually maybe you can make a sort of exploration UI, just like ST has provided for that radio chip I talked about. And this really helped me solve some of the bugs while writing a driver for this, because you could actually connect this to a real chip to a real chip and see all of the values that are changing, and yeah, that's incredible for debugging. I could also send messages using this UI. So I knew I had one radio like sending proper messages, so I could test the receive function on my other radio with my own code. So this is a talk about device driver, but really as a takeaway, I want you to know that like we can have better things. And that's really what the story of Rust is all about. Lots of tooling. And a lot of the talks given today and also yesterday are really about this. A lot of the talks are not about the language. Like there was a talk about Arial OS. And Arial OS is like tooling to make things nicer and better to work with. But we do need to make it. So somebody needs to spend the effort. So I just want to say, like, if you run into anything where things might not be as great as they could be, just create something and release it. My first version was not perfect, far from it. My current version is not perfect. But at least I made it a little bit better than how I found it. So make tools. That's really all I have to say about this. I'd love it if you try it out. I'd also love to talk about it for any questions. There are some QR codes. So on the right is a link to the GitHub where you can find more information, including a link to the book. And on the left, like maybe if you want to read some of my blogs, you can go there as well. Thank you very much.
Awesome. I'm definitely going to try that out. And I would love to see video. Q&A time. Let's start down here and work our way.
Thank you. That's really awesome. I also think you accidentally showed one very underrated and cool feature of the Rust project, which is Rust Doc. So it's really even more excellent if you don't only have the functionality to being able to do that, but also have automatically great documentation generated for that, so people can actually figure out what is supported, how do you use it, what do you have.
Yeah, so that's supported all the way through. So here in the YAML, you see this description, and that actually shows up as a doc comment in the generated code. So even in the like specification way on the left, it'll generate it fully.
That was kind of my question, because when you said you went from the in place macros to proc macros, one thing that's unfortunately not quite as great is, so Rust is not really good about working with generated code. So unfortunately, that's a lot of times what we do in embedded Rust, that we basically generate code rather than, writing the code and then just using it. So my question is, did you lose any of the documentation that you had before? Because, if you have the description here, can you basically use the proc macro system to generate the same amount of good documentation as before, or did you lose anything? Does the Rust project maybe need to revisit supporting generated codes better than it did in the past?
Yeah, no, so nothing is lost there. The only real difference is that, but that's mostly a Rust analyzer thing, and like it's really difficult, so I'm not like saying anything bad about them. But like sometimes it's difficult for Rust analyzer to pick up some of the changes in especially YAMLs and JSONs, like external files. Usually it just works, not always. That's the only downside of going to the proc macros. Well, aside from compile times.
Analyzer has a command to rebuild proc macros. That's the reason.
That helps. Yeah, that helps a lot.
So first off, I think this is incredibly cool out of the box thinking. This is kudos for that. Why don't you have more GitHub stars? So the impression that I got is that a lot of the code is proc macro. And from my experience, it's notoriously hard to get into, that's one. But then there's like this whole new alley of learning how to build them well. Like it's so different. And you can make it not different. I think that's one of the lessons. Do you have any insights or lessons learned on how to do this effectively?
Yeah, I think it boils down to this picture. You got to separate things out. So one of the tricks with proc macros is to have your proc macro crate. It has to be its own crate. At least still, I think they're working on that. Yeah. But then do all of the logic in like a normal crate using all of the David Tolnay cinematic universe. And what that allows you to do is like add testing, for example. Now in here, I had to go even further. So like the parsing in front, at least for the DSL, is using syn. And there's still a little bit of syn in the here. But then in the mirror, I've got nothing anymore. And in the layer, also nothing. And by separating this out, I can really let go of the notion of like even being a macro at all. Like this is now a CLI as well. And then only when I output the tokens again, do I use like a little bit of syn again to and quote to like make everything into a token stream again. So that would be my advice. Like really get out all of the data, do your thing then, and then make it tokens again. Yeah.
Awesome, thank you.
So I don't know if Rust currently has annotations for a source file, if you generate something from a different file, but I guess we could easily add if it's not there. Would you support that in your compiler?
So while the error reporting is a lot better than it used to be, I'm not really carrying over spans of like the original source. That's something I would want to do. If it were possible to like emit compiler errors which actually point at like a YAML, I think that would be really cool. I would have to revamp the way I do errors. I should anyways, but yeah, no, that would be really cool. Yeah.
Yeah, thanks for the talk. So a lot of this, like a big part of the project seems to be just to specify, essentially, like to have a machine-readable documentation for all those chips. This kind of raises the question, I mean, there's also other languages which, you know, interact, like Python, for instance, is very popular among these days for prototyping with these chips. I mean, they could also benefit from this code generation. So are there any efforts underway to, you know, kind of decouple the specification of the chips themselves from the Rust part, essentially, so that you know, is there some centralized database where you can find all the specifications in the end, or where you could contribute them to, so that also other projects could benefit from this?
Yeah. So this is a solo project, so it's just me. I have thought about this a little bit, like if we could get manufacturers to actually give us a standardized like way of reading the data sheets, that would be really awesome. Maybe it could even be this standard. I don't know. Maybe something else. I have thought about like adding support for other languages. Like that would mostly be C. So this tool could definitely like spit out C headers as well. It's mostly like if we have the lir at the end and we need to transform it to something, that could be C headers. It's just like somebody needs to do it. Could be me, maybe someone else. And we need to figure out like what's a good format to spit out. So a lot of care has been taken for that in Rust as well, to like provide Rust code that's also very, very good, where the documentation is like nice and stuff. But yeah, I'd definitely be open to that. Maybe that's the way to trick like the embedded ecosystem into providing things we can easily create Rust drivers for as well. So that would be nice.
Hi, thanks for the talk and all your work on this. 2 questions. The first, the example you gave was a device that talks over SPI to provide access source registers. Do you also support memory map devices or like PCI devices or devices with other bus interfaces?
So because the driver takes a trait, which is just like read register, write register, and also for like buffers and commands, all separate traits, it could support pretty much anything. However, for memory mapped devices, everything is built with fallibility in mind. So you could write an implementation that writes to like internal memory. That's fine. It still will return a result, which is like a little bit weird. So it could do it. It's not per se made for it, but it'll work. Yeah.
Okay, but that's not a use case you've currently tried or done.
No, like maybe we could create a mode where it like doesn't do results, and then you just get it. Then it would be fine, I guess. But like nobody has been angry enough or made me angry enough to make that.
And the second question was, in a lot of the microcontroller worlds, SVD files are used to provide the memory map of a device, which has similar kind of information to what you have in your input, like the address of a register, its bit fields, that kind of thing, so maybe some documentation. Have you looked into that and compared that to your input format? Are there similarities, things that could be combined between the two?
There are definitely similarities. I didn't really start with that because I was really inspired by the work that Hannah Brown did. So my work really was a continuation of that and like a liberation from that driver. So I've never really like looked at SVD for this purpose that much. Now, what's different here than from the SVD is that we also have to deal with different buses and addresses. Like an address could be a U8 instead of like a full word. We also have commands, which a lot of chips have, and buffers, and like maybe in the future a bunch of other types of things. So while SVD like does a niche of this, device driver does a little bit more.
Cool. I think we had one over here.
Thanks so much for the work on this, and I will definitely have to try to auto-generate the input that you need from some hardware that I'm generating. In that vein, I often work with stuff that is then, for example, connected via USB. Have you thought about being able to batch reads, writes over the bus in case the bus has high latency, for example?
I don't know what you mean with, like,
So
what would high latency mean in this case?
Yeah, let's say USB is 10 milliseconds latency, give or take. So if I know I have to do 10 register writes and I'm able to serialize them into one data stream or into one USB packet,
yeah,
would that be something you thought about? Or
I have thought about it. I mentioned it in one of the slides as one of the things I want to do, like multi-register reads and writes. But to do that, I'm really gonna need more const generic support because every register is its own type and has its own like buffer specified. So I can get a buffer that way, but I can't make a buffer that like spans multiple registers generically. That's not possible. So I need to be able to have an array of n plus m. And that's not possible yet. So
Cool. Thank you, everyone. That's all we have time for Q&A.
yeah, thank you very much.